Uh, Clustering is not the only form of unsupervised learning. Another form is, and there are many of these techniques, but we only will mention one. Another application of unsupervised learning is for a task that is very important in general, I would say, in data science, and very much needed in a real-world dataset, that is dimensionality reduction. So that's why I said, as the name suggests, this is linked to the issue of plotting four features into a bidimensional space. No? So that's why it makes sense to talk about this now. Dimensionality reduction means exactly what the name tells you. I have some feature set of a given dimension, of a given size, let's say 25 features. I want to reduce the dimensionality of these features. They are too much. Okay? In every data science problem, there are basically two unavoidable dimensions in your dataset: the number of attributes of features, so the number of columns, and the number of rows. Depending on the specific task you are doing and the algorithm that you are using, be it supervised learning or unsupervised learning, there are algorithms that are perfectly fine with huge databases, in the sense of having lots of data samples. And usually the more data samples you have, the better. Okay, so let's say the longer the table, the taller the table, the algorithm is fine. But maybe the algorithm suffers when the number of features increases. So running an algorithm on 20 features or on 200 features may be quite challenging. On the opposite, but I would say less frequent, there are algorithms that may suffer from long data sets, so much more data points, but they don't really care about having too many features. For sure, having too many features is a problem for us humans. Okay, if I want to plot something that has tens of features, that's a problem. But again, most of the problem is not about visualization, because you can always select only some subset of feature, whatever. Most of the issue is actually more or less every algorithm suffers mostly from having too many features. Okay? Just think about a very simple example, a decision tree. If you throw at a decision tree 200 features, it's incredibly difficult to do splits. First, it is extremely computationally demanding, because you need to consider every feature, the split that the feature will create, compare with all the other possible splits, okay? And the more features you have, the more alternatives you have to do splits, the more likely it is that different splits lead more or less to the same situation, so the same Gini index in your children, for instance. So dimensionality reduction usually is a crucial task in data science. Here we mentioned basically two methods, but if I remember well, we will only see one. You can do dimensionality reduction in an unsupervised way, which basically means I don't really know which are the most or least informative features. Try, according to some criteria, usually this is a criteria derived from the theory of information, let's try to figure it out yourself. What are the most informative features? Supervised, obviously, instead, you know what are the most important features, and you are training a model to recognize the most important feature for an unknown dataset. So let's focus only on the first, since we are in the realm of unsupervised learning. Principal component analysis is actually a technique that maps a set of data points with a given number of features to a lower dimensional feature space. So I have a dataset with 4 features. I want to project it into a plane with only 2 features. Okay? Obviously, I don't want to do this randomly. Ideally, I want to do this in a way that preserve, let's say, the original characteristics of the data, the original trend in the data. A simple example, but this is just an example. I have a dataset with 4 features. I want to do PCA to reduce the dataset to 2 features. Okay, but I want to do so in a way that preserves the average value of the features. I want to preserve the original distribution of the data. It is similar to a Gaussian. I still want a Gaussian. Okay, so you want to preserve some statistical property of the original data. Okay, and of course, as the last sentence makes explicit, this is particularly useful when you want to visualize data. I want to visualize data, and it doesn't make sense to arbitrarily pick only a subset of features. My only hope is to do PCA to reduce the number of features to 2, 3 features, 4 or 5 features, and plot them in pairs. Okay. Principal component analysis is basically this problem. Supposed to have n examples, so n data points, n rows in our dataset with p features, p columns. How can we project this p-dimensional space into, let's say, a 2-dimensional space? Obviously, 2 is an arbitrary parameter, okay? But this is just to make it easier. And for instance, we want to preserve the distances. This is particularly relevant for our example that we just saw in clustering, okay? If I find a way to project my 4 features, the sepal length, width, and petal length and width, in 2 artificial features. Obviously, here we are creating, let's say, artificial features in a way that preserves the distances. What does it mean? If 2 points are far away in the 4-dimensional space, I want them to still be far away in the 2-dimensional space. We can do something like that, okay? So we look for the so-called principal components of data, and this is mostly algebraic, geometric stuff, okay? So basically, the interpretation of the problem from the mathematical or geometric point of view is that principal component analysis is an orthogonal linear transformation, okay? That maps the original matrix of data from the original feature space into a lower dimensional space. So if we have our original data set, okay, is X, we want to transform the data applying some metrics. So this is our original data set, n rows and p features. We want to get a data set with the same number of rows, but a reduced number of features. So obviously, from the matrix point of view, we need to do a multiplication with a matrix that has this exact dimensionality, so that every number. So we search for a projection W that, for instance, okay, maximizes the variance within data. This is usually this is generally valid. Whatever the dataset you have, your objective is always the same. I want a lower dimensional space that preserves some property. Let's forget about the specific example of distance, but some property. In general, we need to maximize the variance within that. Because that means that if we manage to do this transformation in a way that maximizes the divergence between data points, okay, it's easier to discriminate the data. So we are not merging data because we are considering only 2 dimensions out of it. You see, this is not a perfect, let's say, solution. You can do errors in doing this. Okay? This is the general idea of principal component analysis, okay? there are many specific algorithms that can actually find the principal components. If I remember well, we look at one. One of the most general algorithms that is applicable more or less always is based on eigenvalues, eigenvectors, and stuff like that. Stuff that I honestly don't remember from my first year of my bachelor degree. So I put here the reference that I always go to look at anytime in my job I need to deal with eigenvectors that I hate, because for some reason that's one of the things that I never learn, like monadic functions or stuff like that. I read them, I got them, and then I forget them in a few minutes. So I won't ask you for eigenvectors at the oral exam. I can't. I don't know it myself, so I can't. But if you want to know the algebra, mathematics, whatever behind, in particular, the second link is the best explanation I found. So let's hope that it's still alive, because that's really the best explanation I found in all of this year. No, that's not alive, so I need to fix this link. Let's try the other one. In this case, also Wikipedia, okay, is a good source, but I always try to find somewhat interactive explanation, okay? Maybe not that you can click stuff and do simulation, but at least some visualization, okay, that always clarify. But in this case, even the first few sections of Wikipedia are a good explanation. There is a good example here. At least to me, it seems quite good. Maybe it's not the same for you. But I will try to fix the other link, because that was a very clever explanation in my opinion. So just the overview, just the tip of the iceberg. We need to build, first of all, the covariant matrix, and this is extremely easy, okay? So you pick all the data points, and you basically compare the coordinates of each data point with the mean of the data points. That's very easy to build a covariance matrix. And the eigenvectors of this covariant matrix, okay, are computed. I don't care about how they are computed, that's the Wikipedia link. Ordered by descending eigenvalues, the largest one is the principal component. Okay, that's the reason why these eigenvectors are used to compute principal component. And again, your hope in doing this, or any other method to calculate the principal components of a given feature set, your hope is that you find a projection that, despite being lower dimensional, okay, so despite reducing the number of features, preserve the characteristics of the data. So if there was, I don't know, a linear trend for predicting something, there is still a linear trend in the reduced space. If there were 3 clusters in the original space, you still have 3 clusters in the projected space. This is the kind of things you hope to preserve. Again, obviously, we have an example on the iris dataset, for instance. So it's quite useful for us. We pick, as usual, the iris dataset. We do the same preprocessing. Now we have the PCA algorithm imported from sklearn. It is in a completely different module, because technically PCA is not a clustering algorithm. It's a general, I would say that is more of a preprocessing step, usually, in your typical data science pipeline. You are looking for 2 principal components. Again, this is the easiest solution. There are ways, there are algorithms that attempts to estimate the number of principal components, okay? But it's not so easy. So I would say that usually in the vast majority of approaches, you know beforehand how many dimensions you want. For instance, in this case, I want to visualize a plot in a bidimensional space. I want two principal components. That's it. The only thing that changes is the method, fit transform. If you remember, we have seen this method, fit transform, for the scaling of features, for maybe not for one-hot encoding, because that's a very easy transformation, but this is the method that works for most kind of pre-processing in scikit-learn library. So we do the fit transform to find our different data set, okay? And now again, we are doing the inefficient way. We are using the inefficient way of plotting, okay? Because we want to check what? We want to compare the projection that we got, okay? The colors of the points, okay? According to our projection. And instead, the markers of the point picking, for instance, 2 arbitrary coordinates out of the 4. So basically, you want to say, is it easier, with this plot, we try to answer the following question. Is it easier to visually see the clusters in the reduced space? Obviously, we hope for yes as an answer. Let's check. So we are taking a random, an arbitrary pair of characteristics. And this is what happens. So we have the colors represent the different labels in the original space, but of that original space, we only plot 2 features out of 4, the last 2, I think. Instead, all the black points that have different markers are the points, the clusters, according to the reduced space. What can we say? It didn't improve too much with respect, for instance, to these 2 features. Because basically we are in the same position. We can say that these dots, see how they moved? Obviously, it's a different feature space. So these objects are probably a cluster, and that's confirmed in the original space. These are very close to each other and partially mixed in, also in the original space. So let's try with another pair of coordinates just to see what happens. Let's pick, I don't know, the first and the last. Why also the PCA projection changes? Well, it changes obviously because the order changes, so the scales change, okay? Again, we didn't really improve too much. Maybe in this comparison, they seem more mixed, okay? But again, they may seem mixed because by plotting other points in a different feature space, we are in a way mixing apples and oranges. So for instance, let's try to plot only the PCA. Let's remove the first part. So we are only plotting the reduced feature space. And as we can see, in the reduced feature space, again, the spheres are quite well separated. The others are not so much. Okay, so at the end of the story, why I'm doing PCA? Okay, one, I'm doing PCA to better visualize the data, fine. But I already found out that in this specific case, the visualization didn't really improve too much. But probably a more interesting question is, I'm not only doing PCA for visualizing data. What if I apply clustering in this input space? That is a more interesting thing. Can I apply clustering to the new input space? Yes, I mean, it's a new input space. Who cares? I know that I need to find 3 clusters, but I need to find 3 clusters based on a bidimensional dataset instead of a 4-dimensional dataset. So, an exercise for you could be, take this example, and here, apply clustering on the reduced dataset. Maybe the homogeneity, completeness, MV measures improve. Okay? And so it's a good outcome. Maybe PCA didn't really help in visualizing data, but it helped doing clustering. Okay? Obviously, this PCA technique, we have seen this PCA technique in the context of unsupervised learning because it is an unsupervised learning technique. It's, let's say, sibling in supervised learning will be latent discriminant analysis that is mentioned in the slide. But obviously, you can apply PCA as a preprocessing step in any kind of classification task. I have classification with tens or hundreds of features, of columns. Let's try doing PCA. Okay, maybe it improves. Maybe the performance is still on par, but you reduce the complexity. So you reduce the computational time, for instance. Okay, so PCA in general, for real-world problem, is likely a preprocessing step in which data scientists try to understand whether they can reduce the feature set. Obviously, there are other means. PCA conceptually is not so different. Let's forget about the eigenvalues and whatever, but conceptually, doing PCA is not different in its purpose to plot a heat map, a correlation matrix, okay, a heat map of the Pearson correlation values between all the combinations of your input features, something that we mentioned in the very early slides. That's the same. If there are 2 features that are highly correlated, I can remove one, either one, and reduce the computational complexity of my supervised model. There is 1 feature less. Why using both if they are always highly correlated? Who cares? Just pick one. PCA has the same purpose, basically, trying to reduce the space without altering the statistical and information theoretic properties of the original data. So in purpose, they are very similar. Okay? Well, I guess it makes no sense to start a new topic, which will be, next week, another unsupervised learning method, which is called association rule mining. Okay? So that's it. Thank you, and have a nice weekend.